Hello everybody, welcome to a brief introduction to Haskell. In the next 20 to 25 minutes, I'll go through some of the history of the Haskell language, I'll showcase why Haskell is such a great language, and I'll discuss some of the standout features that really make Haskell different than other languages, and which are unique and very cool, I'll promise you. We'll then move on to an actual code demo, which will show some Haskell code, and we'll be solving an actual Exercism exercise. And we'll finish off by listing some of the resources that you can use to learn Haskell. I'm really excited to show you the beauty of Haskell, so let's get started. Haskell is a purely functional language. It has strong and static typing and is compiled. The history of Haskell is somewhat unique in that it has been designed by committee. Back in the day, there were a lot of functional languages, but many of them were proprietary. So they were closed source and you couldn't add stuff to them. So at a gathering, many of academia and programmers, they decided that there should be one functional language that could replace all the other languages. And they came up with the Haskell standard. So Haskell is actually a standardized language, and there are multiple implementations of that standard. The most well-known implementation is the Glasgow Haskell compiler, which is GHC, but there are others too. One of the goals of the Haskell standard is also to have it be a platform where people could do research on functional languages in. So it's like starting point for more advanced functional programming language research. And it has served that purpose ever since its inception. Even though it has the name that it's only useful in academia, that's actually not true. It has real-world usage too. So, for example, Facebook has been using it in its spam filter detection, and GitHub has been using it for its semantic project, which is the tool that parses all the source code of the different languages in the repositories on GitHub. So it's actually a very cool and practical use of Haskell. Haskell has been very influential on other languages. For example, languages like Elm and PureScript and Unison have all been heavily influenced by Haskell, but you can see influences of Haskell in tons of other languages too. And it has been a trendsetter for a lot of stuff that's being used in the functional world. Let's discuss some of the features that make Haskell such a great language. First and foremost, Haskell is a purely functional language. That means that functions in Haskell are pure functions, and pure functions are functions that don't have side effects. So does Haskell not have side effects? Well, Haskell does, of course, because you want to write to a file, etc. You want to do a network request, but it's handled differently from other languages. Haskell does it in a way in which side effects are captured in the type system. So the functions are still pure and side effects are handled differently. The result of having pure functions is that it's easier for you to reason about your code because functions are very predictable. Same inputs result in the same outputs all the time. And that very fact also makes it very good for the compiler to apply optimizations. A second feature of Haskell that's great is its type system. Its type system is very advanced and expressive and flexible. And oftentimes, if your Haskell code compiles, it's likely correct because the compiler is very, very strict in guaranteeing stuff and helping you prevent making mistakes that you might make in other languages. It also has a very advanced type inference, so it's able to figure out types for you without getting in the way, even though it is a statically typed, strongly typed language. Haskell is also extensible via language extensions, and what that means is that via some magic, you can extend the language. It's almost like a plugin. So you can add new features to the language by having loading a language extension. Examples of these are language extensions that can derive implementations for you. So you're just saying derive something, and then it will basically write all the code for you in the background. So you don't have to write it yourself, which is very powerful. Another very powerful language extension is template Haskell, which allows you to manipulate code via Haskell. So it's like metaprogramming, a bit like macros. And that's also very powerful and gives you a ton of very cool stuff that you can do. Haskell also has some really nice syntactic sugar for things like list comprehensions which allow you to create lists in a very succinct way. They're very familiar to Python users probably, but other languages have them too. But Haskell does it, and it does it in a very nice way. You can also write functions. You make them call infix, so between two operands. And that's something that can be very, very useful in certain cases where it's maybe more legible than having it be the default way. So Haskell allows you to do it via some magic. Syntactic sugaring. And then even, for example, an if then else is actually syntactic sugar for a case statement in Haskell, a case expression, I should say. And that's just one of the examples where Haskell offers you syntactic sugar for writing things in a very legible way that will improve upon the basic constructs that you already have. And then we get to Haskell's huge standard library. There are so many functions in the standard library that if you start coding something, start looking for something in a standard library that does it for you. Very often it is the case that it's already built into the standard library and you can just reuse what's there. There is so much there in the base library that it's almost impossible to know it all. But luckily, you have great search engines also for the standard library that even allow you to search for type signatures. Like I want to search for a function that takes a string and then an integer, blah, blah, blah. You can do a lot of stuff. But if you don't find it, you can go to Hackage. And Hackage is like this huge repository of code that you can use. It's libraries that have been written by other people. And there are thousands of packages, 10,000 of packages that you can use. So there's almost always something for you to use if you know how to search for it. Let's discuss some of Haskell's standout features, so the things that really make it unique. The first thing that I'd like to mention is that Haskell evaluates things lazily. Most other languages by default execute eagerly. This means that, for example, if you declare a variable and then you have an expression to initialize its value, that expression will be executed at declaration time, even if you don't use that value further on. However, in Haskell, if you initialize a binding and there it has an expression, but you never use it to calculate something, it just isn't used, so it's not calculated. And that's a very different way for the Haskell runtime to think about things, to execute things, and you get some really cool stuff performance-wise that you would not get with an eagerly executed language. A second feature that Haskell is renowned for is type classes. They're quite a higher level language construct. They're sort of similar to interfaces, and they allow you to overload things based on different types. So you could have an equality type class, which requires that if a type implements the type class, you have to implement the equals function. So any type can then implement the type class and then implement the equals function. And it's sort of like it opts into the type class. So you can treat it as if it was implementing the type class's functions. So this gives you a way of doing function overloading in a type-safe way. It can be somewhat daunting to start out with, but once you've gotten the hang of the type classes, it's an incredibly flexible thing. And it's built into everything that is in the standard library. So it's really important that you do learn about type classes. And once you do, you will start using them and you'll feel very powerful because you can just do a ton of stuff with very generic code that you could not do else in a different language. And the third one is something that I mentioned before, which is that Haskell has pure functions. So side effects have to be dealt with in a different way. So what Haskell has come up with is that side effects are actually part of the type system. And it has its roots in mathematics, and it's called monads. So Haskell has something that's called monads, and monads allow you to capture side effects within the type system and then allow them to be executed in a way that you can still have pure functions. This is something that you don't find in other languages, except for a couple of languages, and is really unique, and it allows a very firm mathematical basis to be in Haskell, so you can reason about your code more easily and even more formally. I think it's time we start looking at some actual Haskell code. what I'll be doing is I'm taking one of the exercises on the Haskell track named strain, and I'll be solving it and have it pass all the tests. And in the process, I'll do some refactoring to show off different features of Haskell and how you could write things slightly differently so that they're actually a bit more easier on the eye and more idiomatic. So the strain exercise is one where you have to implement two functions, a keep function and a discard function. Both functions take a predicate parameter, which is a function that takes a value and returns a Boolean. Then as the second parameter, it takes a list of values and it will return a new list of values. So in the case of keep, it will only return the values for which the predicate is true. In the case of discard, it only will return the values where the predicate is false. So if we have a list 1, 2, 3, and the predicate is even, then it will only return 2. And if we apply the same logic to discard, you will get 1 and 3. So let's see how we can implement that. So this is Visual Studio Code. I have installed the Haskell plugin, the most popular one. There are several. And this has a language server protocol in the background and linting. And I would highly recommend you installing that plugin because you get a lot of goodness for free. You see here that the keep function actually consists of two parts. One is this line, which has the types defines the types for the keep function. So it says there is a function keep, and that function takes as its first parameter a function is a predicate, so a function from A to bool. Then as its second parameter, it takes a list of values, and as its return value, it returns another list of values. And then the second line is where we can actually implement that logic. So let's start doing that. The easiest way is often to look at the simplest, the base case. And in our case, the simplest case is one where the list is empty. So if the list is empty, we can just return an empty list. We're going to use pattern matching for that. So we can use the case keywords. We're going to say case XS of, and this means we're pattern matching on the list, which is XS. And then we're saying if it's an empty list, then we return an empty list. So easy enough. So let's run stack test. And we have one passing test, so the empty keep test passes. So this was obviously quite straightforward. Now we have to process the other case where the list contains an element. So if the list is not empty, we can use pattern matching to deconstruct the list into a head, which is the first element, and a tail, which are everything but the first element. So if we have the list 1, 2, 3, head is 1, and tail is the list with 2 and 3. So if we have a head and a tail, then we're going to say, well, now we have to decide what we need to do. Because there are now two cases, one in which the predicate matches and one where it doesn't. So that sounds to me like an if statement. So let's try if, which is an expression in Haskell, sorry. So if the function p, which is the predicate, and we can just call it like this and pass it the argument. So this is calling the predicate p with the value head. If that's true, then what do we do? So the element matches the predicate, so we have to keep it. So the list that we return has to include the head element. But the tail of the new list is a recursive call. So what we're going to do is we're going to continue doing this, hey, if the predicate match, but then for the other elements. So that's the tail. So we're going to call keep with the same predicate, but now the list that we're passing to it is the tail. So it's everything but the head element. And this is a recursive call. If you don't know recursion, I suggest you maybe look it up because it's a thing that you have to know before you can actually do this. You would normally not use recursion for these types of simple things because there's a ton of stuff in the base library, but the purpose of this exercise is to do manual recursion, and that's why we have to use it. So we're doing recursive calls, and then we have the else case to consider, which is the predicate doesn't match. And in that case, we just don't include it in the list. So we're going to keep on recursing with the same predicate and the till, but we're not going to add the head. So let's see if we have any tests that are passing now. And we have a lot more tests that are passing. Basically, all the tests are passing now. But is this actually the nicest way that we can do this? Well, it probably isn't. But for now, let's just copy this logic to the discard function. And we're going to tweak this a little bit. Of course, we're not going to call keep, but we're going to call discard. And then the logic for the predicate is inverted, because if the predicate matches, then we discard the element. So that's the else thing that we previously had. So predicate matches, we don't include it in the else list, in the result returning list. And if it doesn't, then we do include it. So let's run this. And we have all the tests passing. So we could call it a day and that will be fine. But let's see if we can spice things up a little bit and rewrite things to be a little bit more nice. So this line of code, that's something that's bugging me. So let's see if we can rewrite this. I'm going to copy this into a comment so that we can see the previous version and the next version that we're going to write. Because this little condition, you can see this as, hey, if this pattern matches and that predicate holds, so that Boolean expression holds, then we're going to do something. So what we can do is, instead of having this PhD here, we're going to do the pipe symbol, then we're going to add the Boolean expression, and then we're going to have it return the thing that we did previously if it was true. So that was it. So this is saying if this pattern matches and this is true, then we're doing this. Now, we also have to handle the case where it's not true, which is our previous code. So we're going to just keep on recursing, but without including the head. And this is the same logic that we had here. Only now we have added the predicate test as a guard. And that's more, I think, more readable. You could argue about it. I like this better. Let's see if it works. Still works. So we're going to remove this and keep this here. Another thing that we can do is actually, instead of having this case be within the function, we can actually do pattern matching at the function level. So we're going to say, hey, we're going to do a second keep function definition above it. And we're going to say the second parameter is an empty list. And then we'll return an empty list. So we can now remove it from this bit. And you can have to look at this like at runtime, it will execute the first, it will try to match the first function definition first. And if it does this, then it will do the second thing. So if it's an empty list, it will match this. Otherwise, it will do this. So let's run our test again. So we didn't break anything. That's nice. And then we can, this is just a bunch of the same pattern matching with a Boolean expression. So there's a different way that we can do this. So one thing that we can do is, instead of having this parameter be accessed, we can do the deconstruction of the list into a head and a tail directly within the parameter. And then you might be thinking, hey, we could do the if thingy again here. But there's another thing that we can do. So instead of, I'll comment this, we're going to remove the equal sign and we're going to add a guard clause. And we're saying, hey, the guard clause is a Boolean expression. So we're saying if p head is true, then we're going to do the thing that we do if the predicate matches. Otherwise, we'll do the thing if it doesn't match. Oh, sorry, this has to be an equal sign. This has to be an equal sign. So this is the same thing. We have made a couple of changes. So we don't have the case statement anymore. Instead, we do the pattern matching of the head and the tail directly in the parameter. And then we have two guard clauses shown that have the logic that is associated with the correct guards. So it still works. Just for your information, what would happen if we do true it still passes all the tests, but we get this blue squiggly thingy. And if you hover over it, you can see that there is linting in the IDE. So what the linter suggested, instead of using true, you use otherwise. So it's the same thing in the end, but it's more idiomatic. So let's use otherwise. Okay, I'm quite happy with this. We have function definition that has that uses the empty list. We can even say, hey, we're not using p, which is actually, if we would browse here, we're saying define but not used p, so it's actually in the list. So what we can do is for the things that we don't use an underscore, and that's more idiomatic because we're not interested in that thing. We're going to say, hey, we are not interested in what's passed there. We're just interested in this, and this should still work. Okay, so we can use this logic in the discard function, but we can also do something else. So instead of duplicating the logic of the discard, we can define discard in terms of keep. So what is the thing that differs between keep and discard? It's the predicate. So in one case, it has to be true. In the other case, it has to be false. So that's the negation of the predicate. So what we can do is we're going to say discard is the same as calling keep with something and the list. And now we're going to have to define something. So we're going to do, instead of having the regular predicate, we're going to do the inversion, so the not. We're going to define a lambda. I'm going to say, hey, this takes one element, x, and then we're going to say if not px. So there's a new anonymous function, takes a single parameter, and the return value is not predicate, which is just what the definition is. So we're going to rerun this, and this actually works. But we have a blue squiggly, and there's a couple of things that we can do. One is that Haskell allows you to create functions from functions. So not px, you can see if we somehow chain not with p, we get a new function that's the inverse. And to do that in Haskell, I'm going to keep this as a comment so that for reference, what we can do is instead of having this, we can say not dot p, and this returns a new function that's the same as calling p and then calling not. So that's absolutely the same thing that we do here, but it's shorter. This might take some time to get used to it, but once you've gotten used to it, you're probably preferring this over being explicit with the parameter. So run this, and it's the same thing. And then finally, the final thing that the linting suggests is that we can omit the final value. So there's an XS at the end and an XS at the end here. And this is the same thing. And if you're struggling with this, I suggest you look at some of the Haskell suggestions for learning that I'm about to tell you why this is the same thing. But the linter is now happy. The tests are happy, and I'm happy. So I hope you've enjoyed this bit of Haskell code, and it shows you that you can that the solution, even with using manual recursion, is still very readable, and it's very concise. So that's one of the things that makes Haskell great. You can do a lot with little code. And then finally, let's discuss some of the resources that you can use to learn Haskell. The first and foremost is, of course, the Haskell track on Exercism. The Haskell track on Exercism has over 100 practice exercises that you can work your way through. And it has a wide range of things that handle concurrency, strings, bitwise operations, and you name it. There's a lot of stuff that you can use Haskell for on Exercism, and I highly encourage you to try it out. And one personal tip is that do check out the community solutions for all the exercises. There are some amazing solutions to exercise that other people have come up with that just blew my mind. And I think they'll blow your mind too, unless you are one of the people that have written those. A second resource that you could use is Learn You a Haskell for Great Good. And this is an ebook, or you can also buy it as a regular book. So you can read it online for free, and it has a lot of things. It goes into things from lists and ranges, and slowly builds up to things like type classes and data structures, etc. So there's so much here, and it has been written in a very pleasant way. So it's somewhat funny. It has nice images, and I found it an invaluable resource while learning Haskell. And the third resource that I'd like to recommend is the Try Haskell interactive tutorial. So this is Haskell in the browser, so I could do an expression here, it will be evaluated. But it also has help, and if I press help, you'll get an interactive tutorial. So it says, hey, let me do 5 plus 7, yay, and it detects that the result is as intended, and then you go through all these little steps to learn how to write Haskell. And it's a very cool and interactive way of learning Haskell. And I think these are some of the best resources that you can use to learn Haskell. There are tons more, of course, and Haskell has been written about a lot, so it's easy enough to find content on Haskell. But with these resources to get you started with, I hope you can try out Haskell and that you find you'll like the language too, just as I do.